Well, good afternoon. Welcome to the web seminar hosted by Exeter.com. This afternoon, or this evening, whatever time it is in your time zone, we're going to be talking about model-based failure prediction. And the bottom line is, how are we going to get good failure rate and failure mode data to do our safety and reliability optimization work? My name is Bill Goebel. I've been around the automation industry for over 30 years. Most of the time I spent working for a manufacturing company in new product development. As part of that job, we would examine and study field failure returns. So I have a lot of experience and many years at looking at field failure returns, and I will explain how I was taught by the quality department to analyze that data. And hopefully then you can understand why I'm a little skeptical about such analysis techniques. Obviously, I work for Exeter. Exeter is a global corporation with offices worldwide. We're a combination of people that have come from certification agencies, hence the Exeter certification market-leading position, from new product development organizations. Hence, we understand the new product development process, and from instrumentation end users, so we understand how instruments are used. I think it's a nice collection of divergent experience that combines together to give a very nice perspective to our customers. Exeter has a number of products, all oriented toward functional safety, cybersecurity, and system availability. We do specific consulting on process safety for end users, control system cybersecurity for end users. Exeter is the market-leading product certification company for IEC 61508 SIL certification. We do a lot of training, including, of course, this web seminar. We have engineering tools to help end users and manufacturers achieve safety for less money. We have reference materials and, of course, our extensive database of field failure studies. And lastly, Exeter administers a professional certification program, the CFSE, through the CFSE Board of Governors. And if you have any interest in getting a professional certification in the fields of functional safety or cybersecurity, go to the cfse.org website. Exeter spends a lot of time and energy in the automation industries, and especially in the process industries, chemical, petrochemical, pulp and paper, and power. We spend a lot of time in transportation with both automotive, rail, and off-road transportation. And we spend time in the nuclear industry, where the methods and techniques are very similar to process industry. Of course, the values and the goals are identical. We want equipment that runs reliably, is secure from cyber attack, and has high system safety. Exeter does publish a lot of reference material. You will find that as we develop new analysis techniques, we will write them up with many examples and put them into a book and make them publicly available. We do not keep our methods secret. They are not proprietary company procedures. Even our databases are available in public books and databases available to anybody that would like them. Now, I did want to briefly mention that anyone who has any questions, you will see a Q&A tab at the top of your screen. Do not hesitate to type in a question. in the Q&A tab in the questions box, and I will look for those, and I typically will hear a little beep on my computer, and I will try to answer your questions immediately. Any time you have a question during the presentation or afterwards, please do not hesitate to ask. All right, I'd like to start by just reminding everyone of the fundamental concepts of the functional safety standards. An engineering process called the safety life cycle, which is meant to protect us against design mistakes. IEC 61508 calls that a systematic fault. It differs very much from a random fault in that it is directly traceable and due to an error in procedures. And the other fundamental concept is a probabilistic performance-based system design, where we must calculate probability of failure, and in particular probability of the safety system failure to perform the safety function, and optimize our designs to meet targets based on risk reduction analysis. And in that way, the designer is free to use whatever level of redundancy, whatever test techniques, whatever new technology might come along. The designer is free to optimize the difference between capital expense and life cycle and operating expense. The designer is free to optimize life cycle cost or not, depending on project goals. The designer is free to use whatever techniques and new technology becomes available. There are many advantages to the performance-based probabilistic approach. But I can certainly tell you that this approach was highly debated during the committee meetings, and there are people, even today, who are fighting it at every opportunity. The primary reason that they use against the technique is the probabilistic approach is based on failure rate data, and the failure rate data is just a bunch of made-up garbage. Obviously, they don't have very much respect for failure rate data. And there are some reasons, of course, why. We're going to talk about those and go from there. Now, I did get a question. Is the sound on? And let me just double check. My dB meter is reading very nicely, so I assume that the sound is on, is being transmitted properly. I am getting feedback that this is working. Would somebody else please comment, is the sound working properly? I do see mark on my status display. There's 2 marks registered. One of them seems to be working, one is not working. Okay, the Q&A box came up. Let me just check. Yes, the sound is working. Yes, I can hear. Thank you very much. I just absolutely wanted to make sure everything was being broadcast perfectly before I continued. All right, thank you all. Well, back to the session. The probabilistic performance-based approach gives us protection against random failures, typically hardware-oriented. And I understand why people could not have faith, because early on, failure rate data was hard to get. The methods used were marginal at best. But fortunately, things are getting much, much better, as you will learn in this web seminar. Why do we need failure rate data? The failure rate data is used during the SIF verification calculation, and there are a number of metrics that we calculate. The bottom line is we need failure rate and failure mode data for each component used in a safety instrumented function. If we have quality information, we will be able to do optimal safety and availability design. Where do we get data? I remember very clearly in graduate school, the instructor or the professor explained to me how to calculate a failure rate based on a set of failure rate data. For each failure that occurred, the time to failure, that primary random variable of reliability engineering, time to failure, TTF, is recorded. The time to failure metric is used as a input to a series of different calculation methods, and typically we calculate a random failure rate during useful life. A number of studies have shown that, in fact, that number does vary as a function of time. Often it's higher at the beginning of the operating life. It drops and continues to drop during operation life, and then at some point it starts to go up rapidly, and that's the point which we call end of life or end of useful life. Failure rates, safety and reliability modeling typically assumes a constant failure rate, which, if the number is chosen properly, is a very conservative assumption that drastically simplifies the math, in combination with an end of useful life. So the two metrics are important for each product: the random failure rate as a function of failure mode, and for safety, it's primarily the dangerous failure rate. And then, of course, the useful life period after which a product should be replaced. Now, when we got into the reality of the world, I learned that the professor in grad school was a wee bit idealistic. That, in fact, data from end-user failure records varies substantially. There are variations in the amount of data collected. There are fundamentally different definitions of failure from site to site and from country to country. I've seen situations where people categorize products and merge different technologies together into one grouping, resulting in failure rate averages that are not reflective of any particular technology. I have seen fault isolation that was not complete. And what I mean by that is someone finds a failure, replaces 3 products because they don't know which one failed, and sends and writes up a failure report on all 3, when in fact it could have been only one of them. Many of the problems result in failure rates calculations that are too high. Some of the problems result in failure rate calculations that are too low. You just never know how these are going to turn out. But in spite of these disadvantages, there's a real plus to an end-user field failure study, and that is simple. It's real data. I can also get failure rate data from manufacturers' field return studies. And it's real data as well, and that's a plus we cannot ignore. However, I will tell you that when I worked for a manufacturer, I was taught by the quality department to look at shipping records. And I was taught to assume that 2 weeks after a product was shipped, it was put into service. Then I could start counting operational hours. I was taught to assume that every failure that was returned to us was a failure, and all failures were returned to the manufacturer. And so I would simply take the number of real failures that came in the door, divide by my estimated number of operational hours, and I can tell you in hindsight I was coming up with wildly good failure rate numbers, because those assumptions I was taught are simply not valid. We looked at those numbers and we thought, wow, we are great, and it made us feel good, but it doesn't mean they're right, and it doesn't mean you should be using these kind of numbers to do safety validation calculations. A manufacturer cannot know for sure what percentage of actual failures are being returned unless there's some metric, or unless the manufacturer takes care of all service and maintenance via contract. And manufacturers have different definitions of what is a failure. I was taught that when a unit was returned, it went through our incoming inspection and test routine, and if the test found a problem, it was marked a failure, and the rest of them were marked not a problem. We didn't mark it no failure found, we just marked it obviously this isn't a failure, and we would not count those. Again, quite optimistic. What if our test routines weren't detecting a real failure? I mean, there are all kinds of realistic scenarios that would result in these kinds of studies producing very optimistic data. Unfortunately, some certification agencies use this data to issue the 61508 certification, and I find that very uncomforting. Third data source, an FMEDA. The plus about an FMEDA is it can provide very detailed and complete information. The negative about an FMEDA is that it depends on the component failure mode and failure rate data. And results, of course, must be recalculated for any given environment. So we have three sources, and they all have pluses and minuses. For those of you who don't know what an FMEDA is, it stands for Failure Mode Effect and Diagnostic Analysis. And the fundamental concept is take a big problem and break it into smaller pieces. If a product is manufactured from 200 or 400 components, if we look at each component, understand which ones are necessary to perform any given function, and get the failure rates for each of the necessary components, it's a lot easier to get the failure rate data for the component than it is for the product. And it's a lot easier to get statistics for the components than it is for the product. It's a classic technique that has been around for decades. I remember the old mill handbook 217F calculations from the 1970s. It's the same concept. Break a big problem into smaller pieces, and it's easier to get an answer. FMEDA does that just like it has for decades. Using a component database with failure rates, failure modes, and useful life for each component, in other words, resistors, transistors, microprocessors, A to Ds, and so forth, for each component, you go through an FMEDA process, and you can then generate the product failure rate. The product failure modes, the failure rates for each failure mode, and the diagnostic coverage capabilities of any automatic diagnostics that are in the product. That's a pretty complete picture. I found over and over again that there were failure modes of a product that no one ever really thought about. Like, for example, on a level transmitter, a pressure transmitter, there's a failure mode for external leakage. Now, that does not impact the safety function, but it might very well be reported as a failure. So by understanding the failure modes of the product, you get a very complete picture of how it performs in a safety instrumented function. The FMEDA is an extension of the classic FMEA technique. FMEAs were developed according to one paper I read in the 1960s. So they've been around for, 50 years? It's Very popular because it's an effective method for finding design problems. And those of you who know what an FMEA is understand that we look at a system one component at a time, or we can look at a product one component at a time. And it is an excellent way to provide the foundation for a detailed failure rate analysis model. If one were to add a quantitative failure rate column and diagnostic coverage columns, the FMEA could be extended into a much more detailed and useful technique for determining failure rate prediction models. And that's where we're going with this. Of course, the biggest negative is that the accuracy of an FMEA depends very much on the accuracy of the component database. Component database must include failure rates and failure mode distributions of every single component. In addition, the useful life of every single component can be used to determine the useful life of a product. And typically these all need to be done as a function of what we call the operating profile, and what I mean by that is the set of environmental variables. Just double checking the questions again. I didn't see anything here. In the last session I got quite a few questions about how does failure rate vary as a function of the operating profile or the environmental conditions. And just to reiterate, the fact is products fail more frequently or less frequently as a function of the environmental stress factors. And these are important variables. They must be considered in the analysis, and I will show you a little bit about how that is done. Now, what about these end-user failure studies? There's some negatives, there's some problems there. But after studying dozens of field failure return reports and performing dozens of field failure studies, the Exeter experiences recognize that the primary difference is in the data collection process. And there are a number of important questions that must be asked before analyzing any set of data. The analyst must completely understand the data collection process. The questions one would ask are, exactly when is a failure report written? And what is the definition of failure? Believe it or not, people have very different definitions. Are the as-found conditions recorded during a proof test? A proof test, what's that? Well, remember that for dangerous failures in a automated safety function, a dangerous failure will not cause the process to shut down. That's a safe failure by definition. Dangerous failures are only known and discovered during what's called a manual proof test. But the way in which you do a manual proof test and the way in which you record the data makes all the difference in the world as to the results, analysis results from manual proof test records. And what were the operating conditions? These are the important questions that we must ask. In one example, a set of proof test records was sent to Exeter for analysis. We sat down, went through the analysis, and it appeared as if this particular product had a very, very good result, a very low failure rate. The failure rate was much lower than the FMEA model predicted. So I visited the test site, the test laboratory, and watched a technician performing the proof test. And what I saw was quite surprising. The technician, before running each test, cleaned up the valve. This was on a mechanical product. Cleaning included disassembly and replacement of all seals and O-rings. I was totally amazed that any product failed after this refurbishment activity was done. The as-found conditions were not recorded. It's no wonder there were very few failures in this set of proof test data. If we had automatically done the analysis with a computer program, or if we hadn't taken the time to completely understand the data collection process, we would have got some very misleading field failure results. Think about that. What should be collected during a proof test? Well, remember that one of the main points, or one of the main things we wish to do, is gather up data for the dangerous failure mode. So we certainly must record the device that failed, including serial number, as found conditions, the failure mode, how did it fail, what are the possible causes, if known, the failure date and time, person who did the replacement or who did the analysis, a work order number, and a date and time the instrument was restored to service. This set of data provides all the information we really need to do a good job with extracting valuable data from proof test records. But if some of these pieces of information are missing, we'll have to work a little harder at extracting useful information. What about manufacturers' field return studies? Of course, the plus is, as I said before, it is real data, and that's good. But calculation methods vary widely. Remember what I told you that I was taught. What is the amount of time between the shipment date and when a product goes into service? Was my previous assumption of 2 weeks valid? I would have to say now, no way. And I'll explain in a minute. You cannot know what percentage of actual failures are returned unless all maintenance is done under contract. And to determine this number at Exeter, we've done a number of surveys of end users, and we've discovered the number varies between, for example, 10 and 70%. Occasionally, there might be a higher rate of return, but I'll talk about that in just a minute. I've also discovered that many manufacturers classify returned items as a failure only if a manufacturing defect has found. Many items were marked not a failure or no problem found. And so we have different definitions of failure, different assumptions made, different calculation methods. I find this is a useful source of valuable information, but it is not a useful source of absolute failure rates and failure modes. One way to improve on it, at Exeter we do rough calculations, but we use information only from the warranty period. We count failures only during the warranty period, and we count operational hours only during the warranty period. We assume a percentage of units returned is 10, 50, or 70%, depending on the cost of the device. And those assumptions are based on surveys that we've done of end users and end user maintenance policy. I've also discovered that some of manufacturers have a power on hours counter in the product. For those products, the time to failure is the power on hours count. And so for those products, we have some highly accurate failure rate numbers that can be used to count to calculate an upper bound on the failure rate. Now, why did I say upper bound? Because typically weaker units fail first. The weaker units have a higher failure rate than most units. And of course, we aren't really giving credit for all the successfully operating units. We're only looking at the ones that have failed. However, I find this power on hours counter to be a valuable piece of information that has helped improve quality of manufacturer field return studies quite a bit. By the way, it was a detailed review of the power on counters, the power on hours counter, that allowed us to come up with a very accurate estimate of what is the time period between shipment and startup. And we found, based on 2 or 3 studies of the power on counters, that 6 months is a very good estimate for process industry applications. I criticize end-user field failure studies and manufacturer field return studies. But that doesn't mean they are worthless. There is tremendously valuable information from both sources of data, especially if this information can be compared with the benchmark results of a hierarchical FMEA model. And that's the essence of what our techniques have evolved to. Now remember that an FMEA produces a product failure rate. We can take end-user field failure studies and manufacturer field return studies, calculate a failure rate, at least an upper bound and a lower bound on the failure rate, and compare. Whenever the comparisons show a significant difference, you can dig into the raw data, find out exactly what the reason is, and update the component database. The results have been valuable in that they have often shown previously unknown component failure modes and variables that impact the component failure rates that were previously unconsidered. I have many examples of where a manufacturer field return study or an end user field return study has found problems that even the international standards did not recognize. All that information is valuable and absolutely goes into the component database. Now, if you think about, what am I talking about? What are the drivers of failure rates? Well, absolutely, the physical materials of the component and the component design impact failure rates. The way a component is used in a product, including any self-heating due to power dissipation, the exposure of the component to electrical stress or any environmental stress, and the product level design related to ambient temperature rise, have everything to do in the failure rate of a component. And what I mean by product level design is, did you put a heat sink on that transistor or not? What is the average operating junction temperature of that microprocessor? Did you seal it up and package it in foam so that it gets much harder, or did you provide a way for the temperature to escape? And that, of course, is not the component design, but the product level design. Then, of course, failure rates are impacted by the way in which a product is used. What environment is it in? What average temperature? How many temperature cycles? How many power cycles? How much humidity, shock and vibration, and so forth? So obviously there are 3 major categories of variables: the component manufacturer, the product vendor, and the end user. Now, how in the world could you ever create a component database that could deal with all these variables? That was one of the main criticisms of the whole probabilistic-based approach, is that many threw up their hands and said, this cannot be done. Well, sorry, but I disagree. It can be done. And it can be done via a number of techniques. And let's talk about them a little more. Environments can be categorized. There are IEC standards showing you the typical and worst case numbers for environmental variables for the industrial process control environment. Given those standards, environments can be characterized, and the environmental variables can be fed into a component level analysis. If it's a simple component, like a resistor, many analytical models are available. If it's a complex component, like a microprocessor, you typically do an FMEA on the component, hopefully in conjunction with one of the component manufacturers. And I can tell you that at Exeter, people like Freescale and Texas Instruments and Analog Devices actively participate in this kind of analysis. And we use the environmental variables in the component analysis, or FMEA, to determine the component database. I see a question. Is it possible to allow for redundancies in the FMEA? The answer is yes, but you do have to be careful because an FMEA only considers one component and one failure mode at a time, much like the original FMEA. The reason for that is if we try to deal with combinations of two failures or more, the analysis explodes into what I've called virtual infinity and becomes truly impractical. However, redundancies in a design can be dealt with by replacing redundant components with a single component and using the common cause failure rate. Common cause failures can be modeled. There's a very simple chart to use for that purpose in IEC 61508 Part 6. And via that simple technique, redundancies within a product can be modeled within an FMEA. Need more information on that? Send me an email. Thanks for the question. Given an electrical and mechanical component database, the FMEA technique can be used, as I've said, to generate product failure rates, product failure modes, diagnostic coverage, and actually even estimate useful life and proof test coverage for manual proof test techniques. There's quite a few things that can come out of this analysis. After dozens of field failure studies of both types, this summer we completed a major field failure study on pressure transmitters with remote seals, such that the total number of unit operational hours has reached over 2 billion. So we're quite pleased with the amount of field failure data that we've been able to get. We have, over the last 10 years, updated the component failure database to constantly improve the model. We've identified and updated the model whenever differences between the model and the results are explained. I had one situation occur the summer before last where we were analyzing a two-wire sensing device. In the process industries, we call that a transmitter. And the failure rate numbers from the manufacturer's field failure study were significantly higher than the FMEA predicted. Given that the FMEA is the benchmark, something is wrong. And we dug into the specific results and discovered that on the screw termination circuit board, the failure rate was much, much higher than predicted. And we dug in another layer deeper and discovered that the diodes had a much higher failure rate than predicted. And it turned out that they were leaking current in the reverse direction. Now, those diodes were on there for purposes of overvoltage protection. And they would conduct when the voltage exceeded the breakdown voltage of the diode. And after a brief period of time in the field, apparently the diodes would start leaking current. Now that's almost completely an irrelevant failure mode for a power supply. I mean, what if it leaks one or 2 milliamps? In a big power supply, who cares? So most people would simply ignore that if those failures were ever detected in the first place in that application. But in this application, leakage across the screw terminals increased the 4 to 20 milliamp current level. And if you have a low trip, that's a dangerous failure because the transmitter current will not reflect the process variable until the process variable is much lower than the trip point. Interesting problem. So we were able to learn that the failure modes of a conventional power diode are and failure modes and failure mode distributions are very different when that diode is used in an overvoltage protection application versus a power supply rectifier. And we've entered that into the new database, and we're accounting for these failures now as we move forward. There are many, many examples of this type over the years, and these are things that even the current international standards do not include. The use of a model does not mean we shouldn't do the best possible job that we can on end-user field failure studies and manufacturers' return failure studies. One must always do the best possible job collecting and analyzing field data. I am terribly skeptical of any automatic computer program that looks at field failure records and generates a failure number for you. I'm terribly skeptical because the computer program does not visit the repair shop. The computer program does not understand the data collection process. I have dozens of stories that I could tell you about the problems that we've discovered when visiting the repair site. But if you do a good job analyzing the data and thoroughly understand how it's collected, you can come up with much better information, and that much better information allows you to upgrade the model more accurately. So by using the model output as your primary data source, unknown issues in the data collection process will not ultimately impact results. You never let a significantly high or low failure rate from a field study impact the model unless there is an explanation and an analysis to support it. And even then, what you do is you use that information to upgrade the model and recalculate results. I really like this model-based prediction methodology that has evolved, and I'm pretty convinced that if we use this type of method, this model can provide absolutely the best data for safety verification and false trip optimization. Reliability engineers can use model-based methods to do performance-based probability analysis and even work on optimizing false trips and life cycle cost optimization. I like the whole idea. If anyone has any questions about the material presented, please do not hesitate to ask. If you think of any questions later on, I'm typing up an email address for you. Please don't hesitate to type up your question in an email and send it to me. Even if your question pops into your head later tonight, tomorrow, or next week. I like email because I can handle it asynchronously. And on those nights when I'm worried about failure rate data and cannot sleep, I'll get up and answer email. Yours included, hopefully. Now, if it takes a while, please don't be concerned. Sometimes I do get quite a bit. Do not hesitate to go ahead and type up any questions you might have right now. I see everybody is hanging in there. I would like to say thank you very much for your attention. I appreciate all the time. I hope you will take full advantage of the Exeter Web Seminar Series, and hopefully we can all work together to make the world a safer place. Since I don't see any other questions for now, I will sign off. Thank you all. Keep safe. Goodbye.